You do not need a new workstation to speed up AI work. You need the right upgrades in the right order. Today, we will rank the 7 that move the needle most, explain when to buy, and give simple specs to aim for. First, RAM. This is usually the best value. If your browser, IDE, and notebooks are paging to disk, everything drags. Target 32 GB as a baseline for AI dev and data work. Go 64 GB if you run multiple local models, heavy vector DBs, or big Spark jobs. On laptops, prefer 2 sticks in dual channel. On desktops, keep ranks matched and check your board's QVL so high-speed kits stay stable. Pattern interrupt. If your fans are calm but your system feels slow, it is probably memory pressure, not CPU. Second, VRAM on the GPU. Model size and batch size love VRAM. For everyday fine-tuning, image work, and mid-sized LLMs with quantization, 12 to 16 GB is livable. For larger context windows or heavier vision tasks, 20 to 24 GB is the sweet spot. More VRAM also reduces time lost to offloading. Watch for power and cooling limits in small cases. If you cannot upgrade the card, use smaller precisions and quantized weights to fit. Clear rule. If you are constantly juggling model sizes or hitting out of memory on normal jobs, VRAM is your limit. Third, SSD speed and capacity. Fast storage turns weights into seconds. Choose NVMe drives with strong sustained writes, not just peak reads. A PCIe 4.0 x4 is already great. PCIe 5.0 helps for very large checkpoints and scratch. Aim for 2 TB so you can keep datasets, checkpoints, and a scratch partition. Look for DRAM cache and good endurance ratings. Keep at least 15% free space for wear leveling. Practical tip. Put temp files and model cache on the fastest drive. Keep your OS on a separate volume so restores are painless. Fourth, an NPU or on-chip accelerator. Many new laptops and desktops include a neural processing unit. It will not replace a big GPU, yet it does free your CPU and improve battery life for always-on tasks like transcription, on-device embeddings, and light vision pipelines. If you spend hours on meetings, note-taking, and background AI helpers, an NPU gives quiet, sustained gains. Treat it as free parallelism. Reality check. For heavy training, you still want a discrete GPU. Fifth, cooling that prevents throttling. Performance is what you can hold for minutes, not what you hit for seconds. In laptops, use a quality cooling pad. Avoid blocking intake and keep vents clean. In desktops, add intake and exhaust symmetry. Upgrade the CPU cooler and use a simple positive pressure setup to reduce dust. Reapply thermal paste on older builds. Small undervolts on CPU and GPU can drop temps and keep clocks higher over long runs. If your renders start fast then slow, cooling is the fix that pays back daily. Sixth, an eGPU for flexible compute. An external GPU over Thunderbolt can be a lifesaver for small form-factor PCs and many Windows laptops. It gives you desktop-class VRAM after hours, then you unhook to stay mobile. Know the trade-offs. Bandwidth is lower than a true PCI slot, so training and massive data shuffles are slower than an internal card. Also note platform limits. As of now, Apple Silicon Macs generally do not support eGPU over Thunderbolt, so check before you buy. Best use, stable inference, prototyping, and light fine-tuning when you cannot fit a big card inside. Seventh, Wi-Fi 7 and network hygiene. If you push datasets to a NAS, train on a remote box, or stream models from the cloud, network speed and latency matter. Wi-Fi 7 adds wider channels and multi-link operation, which reduces jitter during large transfers. Pair a Wi-Fi 7 client with a matching router, place access points well, and prefer Ethernet for stationary rigs. Moving a 50 GB checkpoint in minutes instead of an hour can decide whether you try an idea today or tomorrow. So what is the order of operations? Start with RAM, then SSD, then cooling. Those 3 make every task feel faster. Next pick. Your compute path. Upgrade VRAM if you work local, or add a stable remote GPU workflow if your device cannot take a bigger card. Layer an NPU and Wi-Fi 7 when you rely on background AI and remote syncing. Use an eGPU only when internal options are blocked. A few quick guardrails. Do not pair a top-tier GPU with a weak power supply. Give yourself 30% headroom on wattage. Do not buy a very fast SSD, then mount it in a slow slot. Check your lanes and motherboard map. Do not expect an NPU to replace a workstation GPU. It is a companion. With eGPUs, prefer enclosures that match your card's power draw and length, and keep firmware updated. With Wi-Fi, channel planning beats raw spec. Fewer walls and better placement beat turning on every feature at once. Budget playbooks you can copy. On a laptop with 2 slots, moving from 16 to 32 GB by RAM and adding a fast 2 TB NVMe are high impact for the price. On a compact desktop, a mid-range GPU with 16 to 24 GB VRAM and a better air cooler can double your useful workload. On a shared office network, a Wi-Fi 7 router plus a wired hub for your main rig will save you hours over a quarter. Let us recap. The best bang for buck upgrades are RAM, VRAM, SSD, NPU, cooling, eGPU, and Wi-Fi 7. Buy in that order based on symptoms. Keep your builds balanced and your thermals under control. Your actionable next step: open your system monitor, run a typical workload for 10 minutes, and write down the bottleneck you see. Fix that one first. The win is real-time back every single day. If this helped, subscribe for more practical gear guides that turn AI from waiting into doing.